Hello everyone, welcome to this presentation. In this video we are going to talk about SPICE modeling of magnetic devices. Firstly, we are going to talk about magnetic circuits, then we will see the SPICE modeling of the different magnetic elements, and finally an example of implementation in LTspice. This presentation is an excerpt from my book Inductors, Variable and Controllable, published by Amazon KDP. As it is well known, a magnetic circuit can be modeled by an equivalent electrical circuit, as it is shown in this slide. In the equivalent electrical circuit, the voltage source corresponds to the magnetomotive force, the current corresponds to the magnetic flux inside the core, and the resistances correspond to the reluctances of the core. So in this case we have two reluctances. One is the reluctance of the core, Rc, which is given by this expression, and the other one is the reluctance of the air gap, which is given by this other expression here. So from this equivalent circuit we can obtain the magnetic flux by dividing the voltage, the magnetomotive force, by the total resistance, and we can also calculate the inductance using this expression, which is the squared number of turns divided by the total reluctance. So we can see that it is very convenient to use this kind of electrical circuits. In a more complex circuit, we can even model a double E core by using the equivalent electrical circuit, using reluctances and using the magnetomotive force, the voltage source that emulates the magnetomotive force of the winding. So in this case we have two external reluctances given by these distances and the corresponding sectional areas. This will be one and this will be the other one. So we have these two reluctances, R2, which in principle are going to be equal, and then we have in the center arm we have this total distance and this gap, so we have a center reluctance R1 and the corresponding air gap reluctance. From this circuit it is very simple to obtain the flux that is going to circulate through the winding, and then we obtain this expression, so we can also calculate the total inductance that is going to be seen from the winding, and here we have the different values of the reluctances. So we see that this is a very convenient way to model the magnetic circuits using these equivalent circuits. If we want to implement this in a SPICE simulator like LTspice, we need to find models for the magnetomotive force, for the reluctances, and for the different elements. So this is what we are going to see in the next part of the presentation. So we start by modeling the air gap, which is a very simple element. The air gap is going to behave like a constant reluctance, so it's a constant resistance in our electrical model, given by the length of the air gap divided by the permittivity of the free space and divided by the cross-sectional area of the core in which we are introducing the air gap. Because we know that we are going to have some fringing effect in the flux that is going through the air gap, we can add this Vg factor, which is the fringing factor. Usually it is a value slightly higher than 1, and it can be used to better model the behavior of the air gap. Here we are showing the modeling of this air gap in LTspice. Here we can see the symbol and the parameters that we are going to have for this element, and just as we can see, we are modeling it with a resistance with a constant value given by this expression. The next element is a linear reluctance, which is very similar to the air gap. A linear reluctance is that in which the permeability of the material is constant. So we have a BH curve like this one. We don't have saturation, and the material is characterized by the total permeability, which is the relative permeability times the permeability of the free space. So in this case, again, we have constant reluctance, which is given by this expression here. We are including the relative permeability and the permeability of free space, then the dimensions of the element, and also we are including a factor here, VO, in case we want to include some correction. Usually this factor, VO, is going to be equal to 1, but we can use it also for more accuracy in case that we are including some other type of material in which we can have also fringing effect. So this is the model in LTspice, the device in LTspice with the different parameters, and as we can see here, we are including or we are modeling this device by using this expression here, which is a constant resistance. We are also including in this device an output here in these two terminals. As we can see here, in these two terminals we have an output corresponding to the value of the magnetic flux density in this element. Using this expression here with this behavioral source EV, we are generating this value, which is the current. So this is the flux divided by the section. So this corresponds to the magnetic flux density. In this way, we can also use this element as a magnetic flux density sensor. The next element is the nonlinear reluctance. The nonlinear reluctance corresponds to a piece of magnetic material in which we are considering a BH curve like this one. In this case, we have a linear region, and then we are considering also the saturation of the material. So the behavior of the material is going to be like this. B is equal to mu T times H, where mu T is the total permeability of the material. And the reluctance is given by this value that we can see here. And we are using for modeling the total permeability of the material this expression here, which is given by the Brouwer's fitting. In this fitting, we have three parameters, K1, K2, and K3, in order to model the behavior of the total permeability. In this case, the model corresponds a reluctance or a resistance, but in this case, the value of the reluctance is going to depend on the magnetic flux density. Here is the implementation of this element in SPICE. We are implementing the reluctance, the equivalent resistance, by using this behavioral voltage source, in which we have this value for the voltage, which is the value of the resistance times the current circulating through it. So if we divide the voltage given by these expressions by the current circulating through it, then we are going to have this value of the equivalent resistance, in which the total permeability is modeled by this variable voltage here, V of mu m. V of mu n is the voltage here, and is generated with this behavioral current source, which implements this expression corresponding to the Brouwer's fitting depending on the magnetic flux density. And the magnetic flux density is generated by this behavioral current source, which or whose value is given by the ratio between the current through this voltage source EM, because corresponds to the magnetic flux, and divided by the cross-sectional area of the material. This slide shows the implementation of this equivalent circuit that we have just seen, and then we can see here all the corresponding implementation So in this case, our device has this parameter, the length of the material, the cross-sectional area, and the parameters K1, K2, and K3 corresponding to the Brouwer's fitting. So the implementation would be like this, and in this case we have also this output in order to generate the magnetic flux density that we have inside the material. Another element that can be useful is the differential nonlinear reluctance. The differential nonlinear reluctance is a small signal reluctance of a given material, in which the reluctance is modeled with these expressions, the length divided by the differential permeability, which is function of the magnetic flux density, and divided also by the cross-sectional area of the material. In order to obtain the differential permeability, we use this expression here, which is obtained from the Brouwer's fitting. The differential permeability corresponds to these expressions, which is the derivative of the magnetic flux density with respect to the magnetic field intensity. So we can say that the perturbations of the magnetic flux density are given by the differential permeability times the perturbation of the magnetic flux intensity. The implementation of this device is exactly the same as the implementation of the previous one, the nonlinear reluctance with the total permeability. So we can see here the implementation corresponding to this element, in which the only difference is the expression given by the permeability, which in this case is the differential permeability of the Brouwer's fitting. Another interesting element in magnetic structures is the permanent magnet. We are implementing here an ideal permanent magnet. We know that usually permanent magnets are operating in the second quadrant of the BH plane, so we are going to model the ideal permanent magnet just as a constant value of the magnetic field intensity. So the behavior of the permanent magnet is going to be like this. The magnetomotive force generated by the permanent magnet is equal to the magnetic field intensity times the length of the magnet. So the implementation in SPICE, it will be like this. We are going to have these two parameters, HM and LM, and then the implementation is just made by using this behavioral voltage source, which is generating a magnetomotive force equal to Hm times Lm. Now let's see the implementation of a winding. We know that in the winding we have the interaction between the electrical field and the magnetic field in the core. So we have these two expressions here. The winding is going to be generated in the magnetic structure, a magnetomotive force given by this expression, and the voltage that we are going to have across the winding is equivalent to this also well-known equation. So we need to implement these two equations, and for this we have this model here in which we are modeling the winding using this behavioral source with a value which depends on the voltage UW. Okay. The voltage UW is at this point here, and it is generated by using this behavioral current source. This behavioral current source is generating a current which is equivalent to the flux circulating through the magnetic structure. This flux goes through the inductor. This inductor is just a way to implement this characteristic, the number of terms times the derivative in time of the flux. We use this series resistance to avoid any convergence problem. And then the last element corresponds to this behavioral voltage source, which is generating a voltage which is equivalent to the magnetomotive force, which is the number of turns times the current circulating through the winding, which is the current through the behavioral voltage source that we have here at the input. In this slide, we can see how to implement this equivalent circuit. The two equations are implemented with this equivalent circuit that we have just seen, and then we are implementing here everything in SPICE. So we can see the different parts corresponding to the magnetic part, the electric part, and also in this case, in this element, we are including the inductance calculation. So here in these two terminals, we have an output that is going to generate a voltage that is proportional to the inductance. This voltage, as we can see, is generated with this expression here, which at the end is given by the total flux divided by the current circulating through the winding. So it corresponds to the value of the inductance. Another interesting element is the two-arm winding, which is a winding like this one in the figure, in which the winding is embracing two arms of magnetic material. These two arms of magnetic material have a different magnetic flux because they are separated by a spacer, and both fluxes are going through the winding. So the equations that we have in this case are like this. We have a magnetomotive force for each of the magnetic elements, and then we have that the voltage across the winding is going to be proportional to the derivative of the total flux, the addition of both fluxes in time. The implementation of this element is very similar to the simple winding. We use the same part in order to emulate the behavior of the electrical part, which is the winding, and then we have two magnetomotive forces in order to generate the fluxes corresponding to each arm of the structure. Here we can see the implementation in SPICE of this element, which is very similar to the simple winding, so I'm not going to enter into more detail. All these elements are available from my website. You can enter following this link here, and then you can go to the section corresponding to resources, and at this link here you can obtain a copy of this library, including all the components that we have just seen. All of them have been developed specifically for using in LTspice simulator. So if you are not familiar with LTspice, you can watch these videos, LTspice 1 introduction and LTspice 2 install libraries and digital simulation, that you can find on my YouTube channel. Finally, we are going to see an example of using these elements and this library. We are going to use as an example this inductor that we have designed in this other video, Power Electronics number 4, entitled Quick Design of Power Inductors. In this case, we designed an inductor with this value, 75 microhenries, with a DC current level of 2 amperes, an AC peak current of 1 ampere, and an RMS current of 2.2 amperes. The operating frequency is 100 kilohertz. This is the wire diameter, and the packing factor is not very important right now for this example. The permeability or the material that we are going to use is N87 with this value of the permeability 2200, saturation level of 0.4, and DC level of 0.3 in this design. We selected a peak AC component of the magnetic flux density of 0.1 with these losses and so on, and the core that we have used is an EFD20 with these parameters for the different dimensions, and these are the output results of the design. So the total number of turns is 24, the air gap length is 0.28 millimeters, maximum DC current 3 amperes, etc. Let's see now the implementation in LTspice. We can see here the schematics. As we can see, here is the winding with 24 turns. This element here corresponds to the reluctance of the core, we have here the length and the cross-sectional area, the relative permeability, and we are using here a linear device, so no saturation is included. And here we have the corresponding air gap with the length of 0.28 millimeters, the cross-sectional area and the fringing factor equal to 1. In this case, we are supplying the inductor with this equivalent circuit, a voltage waveform which has a DC value of 2 volts, an AC peak value of 48 volts, and a frequency of 100 kilohertz, and this series resistance of 1 ohm. So in principle, we have everything ready for the simulation. So we can run the simulation now and see the results. For example, we can see the voltage across the inductor. So will be the voltage at this point here. So this will be the voltage. Let me add another pane and put here the voltage, and we are going to show here the current through the inductor, which is the same as the current through this resistance R1. So we have here both of them, so we can see that it is working pretty well. The average current is going to be 2 amperes as we have seen as we have selected in the design, 2 amperes. And the peak to peak value, I have adjusted the AC voltage to 48 volts. So with this value, the peak to peak current, as we can see here, is equal to 2 amperes. So it's 1 ampere peak current as was selected in the design. We can also see, for example, adding another pane, we can see the magnetic flux density, the voltage at this output here. So we can see that the average value in this case is 200 millitesla. Okay, so it is below to the maximum DC value that we have selected in the design, which was 300 millitesla. And the peak to peak value, we can go here, click and get the peak value, which in this case, as expected, is 200 millitesla. So the peak value is 100 millitesla as it was selected in the design. Finally, if we can check the value of our inductor, we can see the voltage here at this point. So we can add another pane and then add the voltage at this point here. So we have the voltage which is equivalent to the value of the inductance. So if we select here for the cursor, then we can see that the value corresponds to 74.45. Okay, so it's nearly 75 microhenries as expected in our design. So everything is good. In this case, we are using a linear device, so we can increase, for example, the current here to 3 volt. The voltage is 3 volts, so the current is going to be 3 amperes, and run the simulation again. So we can see that everything is okay. We are operating in linear mode. The value of the inductance is the same. And now the average value of the magnetic flux density is 300 millitesla, so it is now reaching our limit. Okay, but because we are using a linear device, then for the reluctance, then we have no effect of the saturation. Now we are going to see another example of the simulation using a nonlinear reluctance to include the saturation effect. So this is the corresponding schematic, now including a nonlinear reluctance here for the magnetic core. The schematic is exactly the same. in the other elements. So here we can see that the length is the same, the cross-sectional area, and the difference is that we are including this constant K1, K2, and K3, which are the values corresponding to the N87 material. So now we can run the simulation and see also the results. We can see again the voltage, add another pane and show the current. So we can see that they are more or less the same. We can measure the average value of the currents, 2 ampere, the peak-to-peak value of the current, which is around 2 amperes, so it's 1 ampere peak. It's pretty much the same. And then we can see the magnetic flux density, adding another pane here. So we also see that it is pretty the same with a sinusoidal ripple and an average value of now 210 millitesla, very similar as before. And we can also add another pane with the value of the inductance. We can see now that the inductance has a little bit of modulation of ripple, but it is very small, this ripple, because we are mostly in linear region, so there is a little change of the permeability around the DC point of operation. So we can see that it goes from 77.85 microhenries to 78.21 microhenries. So it is almost 78 microhenries, which is very similar, but a little bit different of the theoretical value of 75 microhenries. We can increase now the current and see what happens if we increase the average current to 3 amperes now and run the simulation again. So in this case we can see that the waveforms are more or less in linear region again, but now the difference in the maximum and minimum value of the inductance is higher. So we are entering and getting close to the knee of the VH curve, and then having some effect due to saturation. If we increase, for example, going to 4 amperes and run again, then we can see that now we have a huge impact of the saturation in the waveforms. Even in the current, we can see that it is not a linear behavior anymore. We have some distortion in the ripple due to the saturation. The minimum and maximum values of the inductance are very different, from 58 microhenries to 8 microhenries, and the average value is lower, is around 73 microhenries. So it is decreasing as it is expected when we increase the operation close to the saturation area of the VH curve. Let's try, for example, with 5 amperes. So we can see that the situation is even much worse in this case, and the average value of the inductance is now only 67 microhenries. Okay? Very different to the theoretical value expected in linear region. Well, thank you very much for watching this video. This is all for this presentation. I hope that it is useful for you. Please let me know if you have any comment and question, and see you in the next video. Goodbye now.